right now, as you listen to this sentence, the galaxy closest to us is leaving, not slowly, not gently. The Andromeda Galaxy is actually heading toward us at around 300 kilometers per second, and in roughly 4.5 billion years, it will collide with our Milky Way in a gravitational dance of unimaginable scale. But that is the exception. Almost every other galaxy we can observe in the night sky, every spiral, every elliptical, every faint smudge of ancient starlight, is moving away from us. And the farther away they are, the faster they flee. A galaxy 100 million light-years distant races away at more than 2,000 kilometers every single second. A galaxy 1 billion light-years out moves 10 times faster than that, and the most distant objects we have ever detected, sitting near the very edge of the observable universe, are receding from us at speeds that effectively exceed the speed of light itself, not because the galaxies are breaking any cosmic speed limit, but because the very fabric of space between them and us is stretching, inflating, expanding at every point and in every direction, carrying everything along with it like raisins rising in an infinite loaf of baking bread. This is not a metaphor. It is not an approximation. It is the literal, measured, confirmed reality of the cosmos we inhabit. The universe is expanding. It has been expanding since the moment of its birth, some 13.8 billion years ago. And this single discovery, the realization that everything is drifting apart, stands as one of the most profound revelations in the entire history of human thought. It changed our understanding of where we came from, where we are going, and what kind of universe we live in. It overturned 2,000 years of philosophical certainty. It humbled Albert Einstein. It vindicated a quiet Belgian priest whom almost nobody listened to. And it began with a woman who was paid 30 cents an hour to count the brightness of stars on photographic plates in a basement at Harvard. This is the story of the expanding universe. The story of how a handful of brilliant, stubborn, sometimes overlooked human beings peered through telescopes and scratched equations on paper and slowly, painfully, beautifully uncovered the most stunning truth about reality, that the cosmos is not sitting still. It is running, and it always has been. For nearly all of recorded human history, the universe appeared to be a fixed and unchanging stage. The stars wheeled overhead in predictable patterns. The planets wandered among them in orbits that could be calculated centuries in advance. And above it all, the vault of the heavens seemed permanent, eternal, unmoved, and unmoving. The ancient Greeks looked upward and saw cosmic perfection. Aristotle, writing in the 4th century before the Common Era, declared that the heavens were made of a 5th element he called ether, a substance utterly unlike the earth, water, air, and fire of the terrestrial world. The ether was perfect and unchanging, incorruptible and eternal. The celestial bodies embedded within it moved in perfect circles for all eternity, their motions a reflection of a divine and immutable order. There was no beginning to the cosmos, and there would be no end. It simply was. The very idea that the heavens might change, that a star might appear or disappear, or that the arrangement of the cosmos might differ from one age to the next, was considered not just wrong, but philosophically incoherent. Change belonged to the imperfect world below the moon. The heavens were above all that. This idea proved remarkably durable. When Claudius Ptolemy refined Aristotle's cosmology in the 2nd century of the Common Era, he kept the essential picture intact. The Earth sat motionless at the center of the cosmos. The sun, moon, and planets revolved around it on nested crystalline spheres, invisible solid shells that carried the celestial bodies in their appointed paths, and the outermost sphere carried the fixed stars, pinned in place like gemstones on an enormous rotating shell. The entire structure was finite, ordered, and above all, static. This model would dominate Western thought for more than 1,000 years, surviving the fall of Rome, the rise of Christianity, and the long intellectual winter of the European Middle Ages. Even the great upheavals of the scientific revolution did not dislodge this assumption. Copernicus moved the Earth away from the center in 1543, placing the sun there instead. But his universe was still enclosed within a sphere of fixed stars. Kepler replaced circular orbits with elliptical ones, but the cosmos remained bounded and still. Galileo turned his telescope skyward and discovered mountains on the moon, spots on the sun, and moons circling Jupiter. Yet even he did not question whether the universe itself might be changing. And when Isaac Newton, in 1687, published his Principia and revealed the law of universal gravitation, a new and troubling question arose. One that Newton himself struggled with and ultimately could not resolve. The problem was deceptively simple. If every object in the universe attracts every other object through the force of gravity, and if the universe is finite, then all that matter should be pulling inward toward a common center. The stars should be falling toward each other. The cosmos should be collapsing in on itself, and yet it clearly was not doing so. The night sky looked the same year after year, century after century. So what was holding everything in place? Newton recognized this difficulty. In a famous exchange of letters with the theologian Richard Bentley in 1692 and 93, Newton wrestled with the paradox. His proposed solution was that the universe must be infinite and filled with matter distributed more or less uniformly in every direction. In such a universe, every star would be pulled equally from all sides, and the gravitational forces would balance out, leaving everything in a state of equilibrium. It was an elegant idea, but it was wrong. As later physicists would show, Newton's infinite static universe was inherently unstable. The slightest perturbation, the tiniest deviation from perfect uniformity, would cause regions of matter to begin clumping together, triggering a cascading gravitational collapse. But nobody knew this at the time. And so the assumption persisted. Century after century, through the Age of Enlightenment and the Industrial Revolution and the rise of modern science, the static universe reigned supreme. By the dawn of the 20th century, the prevailing view among astronomers was clear and confident. The universe had always existed and would always exist, more or less unchanged, a vast and eternal clockwork. The Milky Way galaxy, that luminous band of stars stretching across the night sky, was widely considered to be the entirety of the cosmos. Some astronomers speculated that the fuzzy patches of light visible through their telescopes, objects called nebulae, might be other star systems far beyond our own. But this remained a minority view. The scientific mainstream held firm. The universe was the Milky Way. The Milky Way was the universe, and it was not going anywhere. It would take the combined efforts of theorists and observers across multiple continents, working through 2 world wars and a revolution in physics, to demolish this picture and replace it with something far stranger, far grander, and far more unsettling. The first crack in the edifice came not from an astronomer at all, but from a patent clerk in Switzerland who was about to turn the entire understanding of space and time inside out. Albert Einstein did not set out to revolutionize cosmology. In 1915, when he completed his general theory of relativity, his immediate concern was gravity. He wanted to explain why objects fall, why planets orbit stars, and why light bends near massive bodies. What he produced was something far more sweeping than he had anticipated, a set of equations that described the very geometry of the universe. The road to general relativity had been long and grueling. Einstein had spent nearly a decade wrestling with mathematics, struggling to generalize his earlier special theory of relativity to include gravity and acceleration. He taught himself the formidable tools of differential geometry and tensor calculus, often working himself to the point of physical exhaustion. In the final weeks of November 1915, racing against the mathematician David Hilbert, who was pursuing similar ideas, Einstein presented a series of lectures to the Prussian Academy of Sciences in Berlin that laid out the finished theory. The field equations he presented were elegant, compact, and staggering in their implications. They described gravity not as a force transmitted across empty space, as Newton had conceived it, but as the curvature of spacetime itself. General relativity is, at its heart, a theory about the relationship between matter and the shape of space and time. The physicist John Archibald Wheeler would later summarize it with beautiful economy. Matter tells space how to curve, and space tells matter how to move. In Einstein's framework, massive objects warp the fabric of spacetime around them, and other objects follow the curves of that warped fabric. The Earth does not orbit the Sun because the Sun is pulling it inward. The Earth orbits the Sun because the Sun's mass has bent the spacetime around it into a shape that causes the Earth to follow a curved path. It is a staggering reconception of the natural world, and its predictions have been confirmed again and again with extraordinary precision, from the bending of starlight by the Sun, first observed during a solar eclipse in 1919, to the detection of gravitational waves by the LIGO experiment nearly a century later. But Einstein quickly realized that his equations had implications far beyond the solar system. In 1917, just 2 years after completing general relativity, he decided to apply his field equations to the universe as a whole. It was an audacious move. No one had ever attempted a mathematical model of the entire cosmos before. Einstein assumed that the universe was filled with matter spread more or less uniformly throughout space, and he assumed, as nearly everyone did, that the universe was static. It was not expanding, not contracting, simply sitting there in a state of cosmic equilibrium. This was not merely a scientific assumption. It was a deep philosophical conviction shared by almost every educated person alive at the time. The idea that the cosmos might have a beginning or an ending, that it might be evolving in some fundamental way, seemed to belong more to theology than to physics. The problem was that his equations would not cooperate. When Einstein plugged his assumptions into the field equations of general relativity, the math told him something deeply unwelcome. A universe filled with matter could not remain static. The gravitational attraction of all that matter would cause the universe to collapse in on itself, just as Newton had feared 2 centuries earlier. Alternatively, the universe could be expanding outward, the gravitational pull slowing the expansion over time. But a universe that simply sat still, unchanging and eternal, that was not among the options the equations permitted. Einstein was troubled. He believed in a static universe, as did virtually every scientist of his era. The idea that the cosmos might be changing, growing, shrinking, that it might have a history and a future fundamentally different from its present. This struck him as bizarre and unnecessary. And so he made a fateful decision. He modified his equations. He introduced a new term, a mathematical constant that he called the cosmological constant, represented by the Greek letter lambda. This constant acted as a kind of anti-gravity, a repulsive force permeating all of space that would precisely counterbalance the attractive pull of gravity and hold the universe in a state of perfect stillness. It worked mathematically. With the cosmological constant in place, Einstein's equations yielded a model of a static, eternal, unchanging universe. He published this model in 1917 in a paper titled Cosmological Considerations in the General Theory of Relativity. It was the first relativistic model of the universe ever proposed, and it was immediately influential. But it was also, as Einstein himself would later recognize, fundamentally flawed. The problem, which Einstein overlooked at the time, was that his static universe was unstable. The Dutch astronomer Willem de Sitter pointed this out almost immediately. If the density of matter in the universe varied even slightly from the value Einstein assumed, the delicate balance between gravity and the cosmological constant would be disrupted. A tiny increase in density would cause the universe to begin contracting. A tiny decrease would cause it to begin expanding. Einstein's model was like a pencil balanced perfectly on its point. In theory, it could stand there forever. In practice, the slightest breeze would topple it. De Sitter went further. He showed that it was possible to construct a model of the universe using Einstein's equations, including the cosmological constant, that contained no matter at all, an empty universe pervaded only by the cosmological constant. And this empty universe did something peculiar. It expanded. If you were to place a particle in De Sitter's universe, it would accelerate away from you. The redshift of light in this model would increase with distance, exactly as if the universe were inflating. De Sitter's model attracted considerable interest in the astronomical community during the 1920s, in part because some astronomers were beginning to notice that distant objects did seem to show redshifts, just as the model predicted. The British astronomer Arthur Eddington, who had done more than anyone to popularize Einstein's relativity in the English-speaking world, was particularly intrigued. He encouraged his students and colleagues to look into the matter further, a suggestion that would bear extraordinary fruit. This was a deeply strange result, and the implications were unsettling. The equations of general relativity seemed to be telling the physics community something that they did not want to hear, that the universe was a dynamic, evolving entity, not a static backdrop for the drama of stars and planets. But few people took de Sitter's empty model seriously as a description of the real universe. After all, the real universe was full of matter, and everyone knew it was static. Einstein's model, despite its instability, remained the standard picture. The cosmological constant held the cosmos in check, and most physicists were content to leave it at that. Meanwhile, thousands of miles away from the quiet offices of European theoretical physicists, the tools were already being assembled that would blow the static universe apart. In the cold, thin air atop a mountain in Southern California, the largest telescope in the world was nearing completion. And in the basement of an observatory in Massachusetts, a woman was counting stars on photographic plates with a patience and precision that would prove more consequential than any theoretical equation. The observations these instruments would enable were about to change everything. But before we can understand what those observations revealed, we need to travel first not to the mountain, but to that basement, a basement at Harvard University, where a woman with failing hearing and a salary barely above poverty was about to hand the world the key to measuring the cosmos. In the late 1800s, the Harvard College Observatory was one of the premier astronomical institutions in the United States. Its director, Edward Charles Pickering, was an ambitious man with a grand vision. He wanted to catalog the positions and brightnesses of every measurable star in the sky, a staggering undertaking that required an enormous amount of painstaking, tedious labor. Somebody had to examine thousands upon thousands of photographic plates, comparing the brightness of stars, recording their positions, and classifying them into categories. Pickering's solution was to hire women, not because he was a progressive champion of equality, though some of his hires would later describe him favorably. He hired women because they were cheap. In an era when women were barred from operating telescopes or conducting independent research at most institutions, Pickering could employ highly educated, brilliant women at a fraction of what he would have had to pay men. They were called computers, a term that in those days referred not to machines, but to people who performed calculations. They were also known, sometimes mockingly, as Pickering's harem. They worked for around 25 to 30 cents an hour, bent over light tables in the basement of the observatory, squinting at glass plates that captured faint pinpricks of starlight from the southern and northern skies. Among these women were some of the most remarkable scientific minds of the early 20th century. Williamina Fleming, who had been hired initially as a maid in Pickering's household, would go on to discover dozens of nebulae and develop a system for classifying stars by their spectra. Annie Jump Cannon, who was nearly deaf, would classify roughly 350,000 stars over her career, more than any other human being before or since, creating a spectral classification system still used today. And then there was Henrietta Swan Leavitt. Leavitt was born on the 4th of July, 1868, in Lancaster, Massachusetts. She was the daughter of a Congregationalist minister, and she grew up in a devout, intellectually curious household. She attended Oberlin College for 2 years before transferring to what would become Radcliffe College, the women's counterpart to Harvard. It was there, in her senior year, that she took a course in astronomy and discovered a passion that would consume the rest of her life. After graduating in 1892, Leavitt spent time traveling in America and Europe. It was during this period that she began to lose her hearing, a progressive condition that worsened throughout her life and would eventually leave her nearly completely deaf. The cause was never definitively identified. She had always been sickly, plagued by various illnesses that required extended periods of rest at her family's home. But her passion for the stars did not waver. In 1895, she returned to Harvard and began volunteering at the observatory, working without pay because Pickering initially did not need to compensate her. She came from a family of independent means, and her willingness to work for free made her a particularly attractive hire for the budget-conscious director. Eventually, in 1902, she received a permanent staff appointment, earning 30 cents an hour, 5 cents more than most of the other computers. Pickering valued her skills highly enough to grant her extended leaves when her health faltered, and even allowed her to work remotely from her parents' home in Wisconsin during her frequent bouts of illness. Those who knew Leavitt described her as serious-minded, hardworking, and selflessly devoted to her family, her church, and her career. Her colleague Solon Bailey would later write in her obituary that she possessed a nature so full of sunshine that to her all of life became beautiful and full of meaning. She never married. She never achieved public fame. She spent her working life in that observatory basement, bent over photographic plates, while the world outside went about its business unaware that a quiet, partially deaf woman in Massachusetts was about to reshape the entire field of cosmology. Pickering assigned Leavitt to study variable stars, stars whose brightness fluctuates over time in regular, periodic cycles. These stars brighten and dim and brighten again, sometimes over the course of a few days, sometimes over several months. The cause of the pulsation was not understood in Leavitt's time. We now know that Cepheid variables are giant stars that physically expand and contract, driven by a mechanism involving the ionization of helium in their outer layers, a process not fully explained until decades later by the astrophysicist Arthur Eddington and others. But Leavitt did not need to understand why the stars pulsated to make her breakthrough. She simply needed to observe the pattern, and she did so with extraordinary care and precision. Leavitt's particular focus was a class of these pulsating stars called Cepheid variables, named after the prototype star Delta Cephei in the constellation Cepheus, where the phenomenon was first identified by the English astronomer John Goodricke in 1784. A Princeton astronomer once described Leavitt with a mix of admiration and condescension as a variable star fiend. But he had no idea just how consequential her star finding would prove to be. Leavitt studied Cepheids in the Small Magellanic Cloud, a satellite galaxy of the Milky Way visible from the southern hemisphere. Because all the stars in the Small Magellanic Cloud are roughly the same distance from Earth, Leavitt could use their apparent brightness as a reliable proxy for their actual luminosity. And as she carefully measured the periods and brightnesses of 25 Cepheids, she noticed something remarkable. In 1908, she published a brief note at the end of a longer paper, almost as an aside. The brighter Cepheid variables, she observed, tended to have longer periods. It was a simple observation, easy to overlook, buried in a dense technical publication. But it was the seed of a revolution. 4 years later, in 1912, Leavitt expanded on her finding. Working with data from both the small and large Magellanic Clouds, she plotted the brightness of Cepheid variables against the logarithm of their periods and found a clear, linear relationship. Stars with longer periods were genuinely brighter, not just apparently brighter. The relationship was tight, consistent, and predictable. She wrote, with characteristic understatement, that a straight line could be readily drawn among each of the two series of points, corresponding to maxima and minima. What Leavitt had discovered is now known as Leavitt's law, or the period luminosity relationship, and its implications were immense. If you know the true brightness of a star, and you can measure how bright it appears from Earth, you can calculate how far away it is. It is the same principle you use when you see headlights on a distant highway at night. If you know how bright the headlights actually are, and you can see how dim they look from where you are standing, you can estimate the distance of the car. Leavitt's Cepheids were cosmic headlights. By measuring the period of a Cepheid's fluctuation, you could determine its true luminosity. By comparing that to how bright it appeared through the telescope, you could calculate its distance. For the first time in human history, there was a reliable method for measuring the distances to objects far beyond the reach of traditional parallax techniques. The universe had just become measurable. Distances that had been the subject of wild speculation and heated debate could now be determined with real precision. All you had to do was find a Cepheid variable, measure its period, and read off the distance. Leavitt herself was not permitted to pursue the full implications of her discovery. Pickering kept her focused on the laborious cataloging work he had assigned her, restricting the kinds of questions she could investigate independently. She never protested, at least not publicly. She continued her work at the observatory with the same diligence and care she had always shown, even as her hearing faded and her health declined. By the time of the 1920 census, the year before her death, a census taker asked Leavitt to state her occupation. Her answer, quietly defiant, was a single word: astronomer. She died of stomach cancer on December 12, 1921, at the age of 53. Heavy rains fell over Cambridge, Massachusetts that evening, hiding the stars she had spent her life studying behind a curtain of clouds. She never knew the full impact of what she had done. In 1925, the Swedish mathematician Gösta Mittag-Leffler attempted to nominate her for the Nobel Prize in Physics, only to learn that she had been dead for 4 years. Nobel Prizes are not awarded posthumously, but her work lived on. It would become the foundation upon which Edwin Hubble built his case for an expanding universe, and the tool with which astronomers would measure cosmic distances for the next century and beyond. Without Henrietta Leavitt's quiet, meticulous labor in that Harvard basement, we might still be guessing at the size and nature of the cosmos. While Leavitt was counting stars in Massachusetts, a quiet astronomer in the dry desert air of northern Arizona was about to stumble onto the first direct evidence that the universe was not sitting still. Vesto Melvin Slipher was born on a farm near Mulberry, Indiana, on November 11th, 1875. He was one of 11 children, 9 of whom survived to adulthood, born to Daniel Clark and Hannah App Slipher, and he spent his early years working the land alongside his siblings, learning the techniques of agriculture and animal care that sustained the family. He had a younger brother, Earl Carl Slipher, who would also become an astronomer. In the hours not spent tending to crops and livestock, the two brothers developed an early fascination with the night sky that stretched unobstructed above the flat Indiana farmland. Vesto was not a flashy scientist. He was not a self-promoter. He published carefully, worked methodically, and rarely sought the spotlight. After attending high school in nearby Frankfurt and briefly teaching at a country school, he enrolled at Indiana University in Bloomington, where he studied mechanics and astronomy. One of his professors, John Miller, turned his interest toward the stars. Another, Wilbur Coggeshall, who had worked at the Lowell Observatory a few years earlier, introduced him to the idea of heading west to Arizona. After earning his bachelor's degree in 1901, Slipher accepted a position at the Lowell Observatory in Flagstaff, Arizona. Percival Lowell, the observatory's founder, intended the arrangement to be temporary. He wrote to Coggeshall that he would be happy to have the young man come, but that he would not want another permanent assistant. Slipher's temporary assignment would last 53 years. Slipher's boss was Percival Lowell, a wealthy Bostonian who had founded the observatory largely to study Mars and search for evidence of Martian canals. But Lowell also had a secondary interest. He wanted Slipher to study the spiral nebulae, those mysterious fuzzy patches of light that dotted the sky. Lowell suspected that the spirals were nearby gas clouds in the process of condensing into new solar systems. He wanted Slipher to use a spectrograph to measure any rotation or internal motion within them. A spectrograph is a device that splits light into its component wavelengths, producing a rainbow-like spectrum crossed by dark absorption lines or bright emission lines at specific positions. These lines correspond to the chemical elements present in the light source, and their precise positions serve as a kind of fingerprint. Every element in the periodic table produces a unique pattern of lines. Hydrogen has its own signature. Helium has another. Sodium, iron, calcium, each leaves its own characteristic mark on the spectrum. When you look at the light from a distant star or nebula and spread it out with a spectrograph, you can read those lines like a barcode and determine what that object is made of, even if it is millions of light years away. It is one of the most powerful techniques in all of astronomy, and it reveals something even more remarkable than chemical composition. Critically, if the source of light is moving toward or away from the observer, the lines will shift from their expected positions. If the source is approaching, the lines shift toward the blue end of the spectrum, toward shorter wavelengths. If the source is receding, the lines shift toward the red end, toward longer wavelengths. This is the Doppler effect, the same phenomenon that causes the pitch of an ambulance siren to rise as it approaches and fall as it moves away. You have almost certainly experienced this in everyday life. A car horn sounds higher as it rushes toward you and lower as it drives past. The same principle applies to light, except instead of hearing a change in pitch, you see a change in color, and the amount of the shift tells you how fast the source is moving. A small shift means a slow velocity. A large shift means a fast one. By measuring the precise displacement of spectral lines, an astronomer can determine the speed at which a distant object is approaching or receding, even if that object is so far away that it appears as nothing more than a faint smudge of light in the eyepiece. This technique, known as spectroscopy, would become the key that unlocked the expansion of the universe. But in 1901, when Slipher first arrived in Flagstaff, nobody knew that yet. Slipher was a reserved, reticent, cautious man who shunned the public eye and rarely even attended astronomical meetings, often sending his papers for others to read. He consistently postponed publication of his discoveries until he had confirmed them to his own satisfaction. He had married Emma Rosalie Munger of Indiana in 1904, and the couple set up a home at the observatory atop Mars Hill on the western edge of Flagstaff. They had 2 children, Marcia Frances and David Clark. Slipher was not only an accomplished observer, but also an astute businessman and a prominent member of the Flagstaff community, eventually helping to found the town's first high school and its Museum of Northern Arizona. But his real passion was at the eyepiece of the Clark refractor, coaxing faint slivers of light from distant celestial objects onto photographic plates. In 1909, Percival Lowell directed Slipher to begin recording spectra of the spiral nebulae. Lowell hoped the spectra would reveal similarities to our solar system, supporting his own theories about planetary formation. The task was brutally difficult. The nebulae were extraordinarily faint, and the spectrograph required enormous amounts of light to produce usable results. Slipher consulted with astronomers at other observatories, experimented with faster lenses and new observing techniques, and spent 3 years perfecting his approach before he felt confident enough to measure anything. Finally, on September 17, 1912, Slipher exposed his first plate on the Andromeda Nebula. He followed with better plates in November and December, and then over the final nights of the year, on December 29th, 30th, and 31st, and into the pre-dawn hours of New Year's Day 1913, he obtained his best results yet. Over the first half of January, he carefully measured the plates. The result was astonishing. The Andromeda Nebula was hurtling toward the Earth at roughly 300 kilometers per second. This was 3 times faster than any previously known object in the universe, roughly 15 times the average velocity of a star. It was a velocity so extreme that Slipher himself could scarcely believe it. But the data was clear. He presented his findings at a meeting of the American Astronomical Society in August of 1914, and the audience gave him a standing ovation. One of the very few times in the Society's history that such a thing had occurred. But Slipher did not stop with Andromeda. Over the following years, he measured the radial velocities of more and more spiral nebulae, and a striking pattern began to emerge. While a handful of nebulae, like Andromeda, showed blue shifts, indicating they were approaching, the vast majority showed redshifts. They were moving away, and some of them were moving away very fast indeed. By 1917, Slipher had measured the radial velocities of 25 spiral nebulae. All but 3 showed redshifts. The average recession velocity was roughly 570 kilometers per second, an enormous speed that set the spiral nebulae apart from any known class of celestial object. By 1923, his sample had grown to 41, and 36 of them were racing away from us. Slipher did not fully grasp the cosmological significance of what he was seeing. He interpreted the data as evidence that the entire solar system, and indeed the whole Milky Way, was drifting through space relative to the spiral nebulae. He calculated a mean velocity of roughly 700 kilometers per second for our galaxy's motion through the cosmos, and he made a remarkable intellectual leap. Since the stars in the Milky Way did not show this motion individually, the entire stellar system must be moving as one. This observation, he noted, lent support to the idea that the spiral nebulae were distant stellar systems in their own right, not small nearby clouds. It was an insight that came a full 8 years before Hubble would settle the question definitively by resolving individual stars in Andromeda. But Slipher did not connect the redshifts to a universal expansion. He did not plot velocity against distance, because reliable distance measurements for the nebulae simply did not exist at the time. He recorded his observations with his characteristic precision, published them in the Lowell Observatory Bulletin and the Proceedings of the American Philosophical Society, and waited for someone else to provide the distances that would unlock the full meaning of his data. The irony is that Slipher had in his hands the most important dataset in the history of cosmology. Virtually every person who would later work on the expansion of the universe, from Georges Lemaître to Edwin Hubble himself, would rely on Vesto Slipher's redshift measurements as a crucial piece of the puzzle. Hubble's famous 1929 paper, in which he announced the velocity-distance relationship, used velocities that were almost entirely Slipher's measurements, though Hubble cited them only in a footnote. Lemaître's earlier 1927 paper, which independently derived the same relationship, also relied on Slipher's data. The expansion of the universe was discovered, in a very real sense, with the redshifts that a quiet Indiana farm boy had measured with a temperamental spectrograph on a 24-inch refractor in the Arizona desert. And yet Slipher remains one of the least recognized figures in modern cosmology. His name is largely absent from textbooks and popular accounts. A biographical memoir written after his death by the National Academy of Sciences noted that Slipher probably made more fundamental discoveries than any other observational astronomer of the 20th century. He retired from Lowell Observatory in 1954. After 53 years of service, the same institution that Percival Lowell had told him would be a temporary arrangement. He died in Flagstaff on November 8, 1969, 3 days before his 94th birthday. He deserves to be remembered. While Slipher was measuring redshifts in Arizona, a controversy was building in the world of professional astronomy that would eventually draw in nearly every major figure in the field. The question was deceptively straightforward. How big is the universe? More specifically, the debate centered on the nature of those same spiral nebulae that Slipher was studying. Were they relatively small objects within our own Milky Way galaxy, clouds of gas and dust caught in the gravitational web of our home system? Or were they something far grander, independent collections of billions of stars lying at enormous distances beyond the Milky Way? What the 18th century philosopher Immanuel Kant had poetically called island universes. The idea of island universes had been around since the 1750s, but it had fallen in and out of favor over the decades. By the early 20th century, opinion was sharply divided. On one side were those who believed the Milky Way was essentially the entire universe, with the spiral nebulae as minor features within it. On the other side were those who suspected the spiral nebulae were vastly distant galaxies in their own right, which would mean the universe was far larger than anyone had imagined. The tension came to a head on the evening of April 26, 1920. In the ornate Baird Auditorium of the Smithsonian Institution's National Museum in Washington, D.C., two astronomers took the stage to argue their opposing views in what would become known as the Great Debate. It was one of the most famous intellectual confrontations in the history of science, though at the time it was neither well publicized nor particularly well attended. Most of the audience that night were members of the National Academy of Sciences, and the majority of them were not astronomers. The debate was the topic of that year's William Ellery Hale Lecture, a series endowed by the father of the great telescope builder, George Ellery Hale, and the organizers had considered several other topics before settling on the distance scale of the universe. The alternatives included Einstein's theory of relativity, the causes of ice ages, and even a topic in zoology. The format was straightforward. Each speaker would present his case for 40 minutes, followed by a brief period of discussion. There was no audio amplification in the auditorium, a fact that would prove consequential. On one side stood Harlow Shapley, a young, ambitious astronomer from the Mount Wilson Observatory in California. Shapley was just 34 years old, nervous, and acutely aware that a poor showing could damage his chances of winning the directorship of the Harvard College Observatory, a prize he desperately coveted. He had an unlikely backstory. Born near Nashville, Missouri, he had started his career as a newspaper reporter covering crime stories. In 1907, he had arrived at the University of Missouri intending to study journalism, but the program had been postponed, so on a whim he flipped through the course catalog, saw that astronomy came first alphabetically, and enrolled. From that accidental beginning, he had risen rapidly to become one of the most promising young astronomers in America. Shapley had recently used Cepheid variable stars, building on Leavitt's discovery, to map the distribution of globular clusters around the Milky Way. His measurements suggested that our galaxy was far larger than previously believed, perhaps 300,000 light-years across, with the Sun located not at the center, but far out toward the edge. If the Milky Way was this enormous, Shapley argued, there was no need to invoke island universes. The spiral nebulae could easily be small objects within or near our own galaxy. On the other side stood Heber Doust Curtis, a man 13 years Shapley's senior and far more experienced at public speaking. Curtis was a curious figure in astronomy. He had originally trained as a classicist, teaching Latin and Greek at a high school in California, before a growing fascination with the night sky drew him into science. He eventually earned a doctorate in astronomy and became one of the leading researchers at the Lick Observatory atop Mount Hamilton. Curtis was a confirmed pipe smoker who had a habit of accidentally setting his wastebasket on fire, and his fearsome oratory skills, honed from years of classroom teaching, made him a formidable debate opponent. In the lead-up to the event, when Shapley tried to reframe the confrontation as a gentle discussion. Curtis had pushed back with characteristic directness. He wrote to Shapley that they could be just as good friends if they did go at each other hammer and tongs, adding that a good friendly scrap was an excellent thing once in a while, since it cleared up the atmosphere. Curtis maintained the older, more conservative view that the Milky Way was only about 30,000 light-years across, with the Sun near its center. But he compensated for this smaller galaxy with a radical claim. The spiral nebulae were independent galaxies comparable in size to the Milky Way, lying at immense distances. Curtis pointed to several lines of evidence. He noted that the spiral nebulae contained far more novae, exploding stars, than one would expect if they were merely small clouds within the Milky Way. He pointed to the high radial velocities measured by Slipher as evidence that the nebulae could not be gravitationally bound to our galaxy. And he drew attention to the dark lanes of dust visible in Edwin spiral nebulae, which looked strikingly similar to the dust lanes in our own galaxy. If the faintest spiral nebulae were truly independent galaxies, Curtis realized they would have to be at distances on the order of 100 million light-years, a figure that strained the imagination, but was not, he argued, impossible. Each man was given 40 minutes to present his case. Shapley went first. He read from a prepared script, delivering a broad and somewhat general overview of his work on the Milky Way's size. Most of his lecture focused on the vast dimensions of our home galaxy, with the argument about spiral nebulae coming only toward the end. Curtis followed with a more technical presentation, projecting typewritten slides that laid out his evidence point by point with clarity and force. He spoke with the practiced confidence of a man who had spent years commanding classrooms, and his ability to project his voice across the unamplified auditorium gave him a decisive advantage over his more soft-spoken opponent. The discussion was moderated by Princeton astronomer Henry Norris Russell, and some accounts suggest, though this has never been confirmed, that Albert Einstein himself was in the audience that evening. Neither man convinced the other. Neither man produced a decisive piece of evidence. The great debate ended, as these things often do, in a draw. The audience filed out without resolution. The question of the spiral nebulae remained open, but both Shapley and Curtis were partly right and partly wrong. Shapley was correct that the Milky Way was much larger than the traditional estimate, though his figure of 300,000 light-years was itself too large. Modern measurements place the diameter at roughly 100,000 light-years. He was also correct that the Sun was far from the galactic center, but he was wrong about the spiral nebulae. Curtis, meanwhile, was correct that the spirals were independent galaxies, but his estimate of the Milky Way's size and the Sun's position within it were both off. The great debate would not be settled by argument. It would be settled by evidence. And that evidence was about to arrive, courtesy of a man who had once studied law at Oxford, coached high school basketball in Indiana, and served as a major in the United States Army during the First World War, before finally following his true passion to a mountaintop observatory above the glittering lights of Los Angeles. Edwin Powell Hubble was born on November 20th, 1889, in the small town of Marshfield, Missouri. He was the fifth of 8 children in a family that moved frequently during his youth. Eventually settling in the Chicago suburb of Wheaton, Illinois. From an early age, Hubble displayed two qualities that would define his life: extraordinary athletic ability and an insatiable intellectual curiosity. He was tall, broad-shouldered, and handsome, with a talent for nearly every sport he tried. He excelled at basketball, football, baseball, and track. As a high school student, he once broke the Illinois state record in the high jump. He was also a gifted boxer, and there were rumors, never fully confirmed, that a promoter once tried to arrange a match between Hubble and the world heavyweight champion Jack Johnson. But Hubble's mind was at least as formidable as his body. He devoured science fiction novels, particularly the works of Jules Verne, and he showed early aptitude in mathematics and science. When he entered the University of Chicago in 1906, he studied mathematics and astronomy under some of the leading scientists of the day. He graduated in 1910 and was awarded a Rhodes Scholarship to study at Queen's College, Oxford, where, at his father's insistence, he studied law rather than science. Hubble's time at Oxford left a deep impression on him. He adopted a faintly British accent, a taste for tweed jackets and pipes, and certain mannerisms that his American colleagues would later find either charming or pretentious, depending on who you asked. He returned to the United States in 1913, passed the bar exam, and briefly practiced law in Louisville, Kentucky. But his heart was never in it. After just 1 year, he abandoned the legal profession and returned to the University of Chicago to pursue a doctorate in astronomy. Hubble conducted his graduate research at the Yerkes Observatory in Williams Bay, Wisconsin, studying the faint, fuzzy patches of light called nebulae. His dissertation, completed in 1917, was titled Photographic Investigations of Faint Nebulae. It was solid, competent work, but it did not yet hint at the revolutionary discoveries to come. Before Hubble could begin his career as a professional astronomer, the First World War intervened. He enlisted in the Army, received a commission as an officer, and served in France with the 343rd Infantry Regiment of the 86th Division. He rose to the rank of major and saw combat, though the details of his wartime service are somewhat murky. Hubble had a well-documented tendency to embellish his personal history. When the war ended in 1918, he was discharged and immediately headed west to the place where his destiny awaited. Mount Wilson Observatory sat at an elevation of roughly 5,700 feet in the San Gabriel Mountains, above Pasadena, California. It had been founded by the tireless astronomer George Ellery Hale, who had an extraordinary talent for convincing wealthy donors to fund the construction of ever larger telescopes. The jewel of Mount Wilson was the Hooker telescope, a reflecting telescope with a mirror 100 inches, 2.5 meters in diameter. When it was completed in 1917, it was the largest and most powerful telescope in the world, and it would hold that distinction for 3 decades. Hubble arrived at Mount Wilson in 1919, a 30-year-old man who still bore the bearing and habits of a soldier. He quickly impressed his colleagues with his energy, his observational skill, and his almost obsessive dedication to his work. He spent long, cold nights at the Hooker telescope, guiding the massive instrument by hand as it tracked celestial objects across the sky. exposing photographic plates for hours at a time to capture the faintest possible light from the most distant objects. His first great triumph came in October of 1923. Hubble was photographing the Andromeda Nebula, that same bright spiral that Slipher had measured rushing toward us a decade earlier. He was using the full power of the Hooker telescope's 100-inch mirror, its light-gathering ability unmatched by any other instrument on Earth. As he compared his latest photograph with earlier images, he noticed a faint point of light that had changed in brightness. At first, he marked it as a nova, a type of exploding star, writing N on the photographic plate with a pen. But on closer examination, as he compared more plates taken over successive nights, he realized the star was not a nova at all. It was something far more valuable. It was brightening and dimming in a regular, periodic cycle. He crossed out the N and wrote the letters VAR with an exclamation mark. It was a Cepheid variable star, a Cepheid in Andromeda, the single most important speck of light in the history of astronomy. The significance was immediate. Using Leavitt's period luminosity relationship, Hubble could now determine the distance to the star, and by extension, the distance to the entire Andromeda Nebula. He measured the Cepheid's period at 31.45 days, which told him its true luminosity. Comparing that to its apparent brightness, he calculated a distance of roughly 900,000 light-years. Later corrections, accounting for the existence of two types of Cepheid variables with different luminosity calibrations, would revise this distance upward to approximately 2.5 million light-years. The Cepheid that Hubble identified is still known today as Hubble Variable Number 1, or VONE, and the Hubble Space Telescope imaged it in 2011 as a tribute to the discovery that started it all. 900,000 light-years. The Milky Way, even by Shapley's generous estimate, was only 300,000 light-years across. The Andromeda Nebula was far, far beyond it. It was not a cloud of gas within our galaxy. It was another galaxy entirely. A vast, independent system of stars comparable in scale to the Milky Way itself. Hubble had settled the great debate. The spiral nebulae were island universes. The Milky Way was not the entire cosmos. It was just one galaxy among, well, nobody knew how many. But clearly, there were a lot. Hubble communicated his results first in a letter to Shapley. When Shapley received the letter, he reportedly turned to a colleague, the young astronomer Cecilia Payne, and said, with a mixture of shock and resignation, "Here is the letter that destroyed my universe." Hubble formally presented his findings at a joint meeting of the American Astronomical Society and the American Association for the Advancement of Science on January 1st, 1925, in Washington, D.C. He was not even present at the meeting. He had sent his paper to be read by another astronomer, preferring to remain at Mount Wilson to continue his observations. The New York Times reported the news on its front page the following day, and the ripple of astonishment spread quickly through the scientific world. The universe had suddenly become unimaginably larger, and Hubble was just getting started. Having proved that galaxies existed beyond the Milky Way, Hubble turned to a new question. What were those galaxies doing? Were they simply sitting out there in the void, separated by immense distances, but otherwise motionless? Or were they moving? The tools to answer this question were already in hand. Slipher's redshift measurements, accumulated over more than a decade, showed that the vast majority of spiral nebulae, now understood to be galaxies, were racing away from us, but Slipher's data had a critical limitation. He had measured the speeds of the galaxies from their redshifts, but he did not have reliable distances for most of them. Without knowing both the speed and the distance of each galaxy, it was impossible to see whether there was a systematic relationship between the two. This is where Hubble's work at Mount Wilson became crucial. Using the Hooker telescope, Hubble painstakingly measured the distances to as many galaxies as he could, primarily by identifying Cepheid variables within them and applying Leavitt's period luminosity law for more distant galaxies where individual Cepheids could not be resolved. He used other, less precise distance indicators, such as the brightness of the most luminous stars in the galaxy or the overall apparent brightness of the galaxy itself. Hubble was aided in this effort by Milton Laezel Humason, a remarkable figure in the history of astronomy. Humason had no formal education beyond the 8th grade. He had dropped out of school as a teenager to work as a mule driver, hauling lumber and construction materials up the steep, winding road to the summit of Mount Wilson during the construction of the observatory. The work was grueling. The road climbed more than 4,000 feet in elevation over about 9 miles, with switchbacks so tight that the mules sometimes lost their footing on the crumbling edges. Humason loved it. He loved the mountain, the clean air, the silence, and the stars that blazed overhead at night with an intensity that the city lights of Lowe's angels far below could not touch. After a brief stint as a farmer, Humason returned to Mount Wilson, this time as a janitor and general handyman. He swept floors, maintained equipment, and gradually made himself indispensable when the astronomers needed a night assistant to help with their observations. Humason volunteered. His natural skill with the delicate instruments, his steady hands, his infinite patience, and his intuitive feel for the telescope's behavior quickly set him apart. He was promoted, step by improbable step, from janitor to night assistant to full-fledged staff astronomer, despite never having attended a single college course. Humason's specialty was spectroscopy, and his ability to obtain spectra of extremely faint and distant galaxies was unmatched by any astronomer of his era. The work was punishing. To capture enough light for a usable spectrum from a galaxy millions of light years away, Humason sometimes had to expose a single photographic plate for 30, 40, even 50 hours, spread across multiple consecutive nights. Throughout these marathon exposures, he had to guide the massive telescope by hand, his eye pressed to the eyepiece, making constant, tiny adjustments to keep the telescope precisely trained on the target as the Earth turned beneath it. The dome was unheated, and on winter nights, the temperature inside could drop below freezing. Humason sat in the cold and the dark, hour after hour, adjusting and waiting and adjusting again, coaxing slivers of ancient light onto glass plates. He would go on to measure the redshifts of galaxies so distant that the light reaching his photographic plates had left its source hundreds of millions of years in the past. Together, Hubble and Humason assembled a dataset of galaxy distances and velocities that, while small by modern standards, was sufficient to reveal a stunning pattern. In January of 1929, Hubble submitted a paper to the Proceedings of the National Academy of Sciences titled "A Relation Between Distance and Radial Velocity Among Extragalactic Nebulae." In it, he presented data on 46 galaxies, though only 24 had independent distance measurements, and plotted their velocities against their distances. The plot was rough. The scatter was considerable, but the trend was unmistakable. There was a direct, linear relationship between a galaxy's distance and its speed of recession. Galaxies twice as far away were moving twice as fast. Galaxies 3 times as far away were moving 3 times as fast. The universe was not static. It was expanding. And it was expanding in a remarkably regular, orderly fashion. This relationship came to be known as Hubble's law. It can be expressed in a simple equation. Velocity equals a constant, the Hubble constant, multiplied by distance. The Hubble constant describes the rate of expansion, how fast the universe is stretching at any given distance. Hubble's original estimate of this constant was approximately 500 kilometers per second per megaparsec, a value that later measurements would show was far too high. Modern estimates place the Hubble constant somewhere around 67 to 74 kilometers per second per megaparsec, depending on the method of measurement, a discrepancy that remains one of the great unsolved puzzles in cosmology. It is worth pausing here to understand what Hubble's discovery actually means, because it is profoundly counterintuitive. When we say the universe is expanding, we do not mean that galaxies are flying outward through space, like shrapnel from an explosion, into some pre-existing void. We mean something stranger and more fundamental than that. We mean that space itself is stretching. Think of it this way. Imagine drawing dots on the surface of a balloon with a marker. Each dot represents a galaxy. Now imagine inflating the balloon. As the rubber stretches, every dot moves away from every other dot. No dot is at the center. No dot is at the edge. The expansion is happening everywhere at once, at every point on the surface, and the dots that started farther apart are now separating faster, because there is more rubber between them to stretch. This is a two-dimensional analogy for what is happening in the three-dimensional universe. Space itself is expanding. The galaxies are not racing through space. They are being carried apart by the stretching of space between them. And the farther apart two galaxies are, the more space there is between them, and the faster that space is stretching. And so the faster they appear to be moving apart. This is why very distant galaxies can appear to be receding faster than the speed of light, without violating Einstein's prohibition on faster-than-light travel. The galaxies themselves are not moving through space at superluminal speeds. It is the space between us and them that is growing at such a rate that the total distance between us increases faster than light can cross it. It is a subtle but crucial distinction, and one that lies at the heart of modern cosmology. Hubble himself was cautious about the interpretation of his results. In his 1929 paper, he did not explicitly claim that the universe was expanding. He simply presented the empirical relationship between distance and velocity, and left the theoretical interpretation to others. He was well aware of the theoretical work suggesting that the universe might be expanding, but he was an observer by temperament, and he preferred to let the data speak for itself. Others, however, were not so reticent. And the theoretical framework for understanding Hubble's observations had, in fact, already been laid down, years before Hubble published his paper, by two men who are among the most underappreciated figures in the history of science. Alexander Alexandrovich Friedmann was born on June 16, 1888, in St. Petersburg, the glittering capital of the Russian Empire. His parents were artists, his father a ballet dancer and composer associated with the Imperial Theater, his mother a pianist who had graduated from the St. Petersburg Conservatoire. It was an unlikely background for a man who would become one of the founders of modern cosmology. Friedmann showed exceptional mathematical talent from an early age. He studied at St. Petersburg State University, where he excelled in both mathematics and physics. He formed a lifelong friendship with a fellow student, Jacob Tamarkin, who would also go on to become a distinguished mathematician. After completing his degree in 1910, Friedmann began lecturing at the St. Petersburg Mining Institute, and he quickly established a reputation as one of the most promising young mathematicians in Russia. When the First World War erupted in 1914, Friedmann enlisted in the Russian Imperial Army as an aviator. He flew reconnaissance and bombing missions over the Austrian front in conditions that were often terrifyingly dangerous. Early military aviation was an endeavor that killed many of its practitioners through mechanical failure and enemy fire alike. Friedmann was undaunted. He not only flew the missions himself, but also developed a mathematical theory of bombing that described the optimal trajectory for dropping ordnance from a moving aircraft. He personally verified his calculations during combat flights, combining mathematical precision with physical courage in a manner that few theoretical physicists before or since have matched. He organized the Army's aerological services, setting up networks for collecting atmospheric data that could improve both weather forecasting and flight planning. His wartime service earned him several military awards, including the Cross of St. George. After the Russian Revolution and the chaos of the Civil War that followed, Friedmann returned to academia in the newly renamed Petrograd, a city transformed by revolution and shattered by famine. The intellectual landscape had been upended along with the political one. But Friedmann's mathematical brilliance had only sharpened, and in the early 1920s, he began to grapple with Einstein's general theory of relativity and its implications for cosmology. His interest may have been sparked in part by the growing fame of Einstein's theory following the dramatic confirmation of the bending of starlight during the solar eclipse of 1919, which had made headlines around the world. Whatever the catalyst, Friedmann threw himself into the mathematics of curved spacetime with the same intensity he had brought to bombing trajectories over Austria. And in 1922, he produced a paper that should have changed the world. Friedmann's paper, titled On the Curvature of Space, was published in the respected German journal Zeitschrift für Physik. In it, Friedmann did something that neither Einstein nor de Sitter had been willing to do. He abandoned the assumption that the universe was static. Instead, he solved Einstein's field equations with the most general assumptions possible, allowing the radius of the universe to change over time. What he found was a family of solutions, each describing a different possible history for the cosmos. In one solution, the universe expanded from a singular point and continued expanding forever at a decelerating rate, eventually reaching an inflection point and then accelerating. In another, the universe expanded and then contracted, oscillating back and forth in a cycle of cosmic expansion and collapse. In a third, the universe expanded from a finite initial size and grew exponentially without limit. The key point was that a static universe was merely one special, unstable case among many dynamical possibilities. The natural behavior predicted by Einstein's equations was a universe that changed. This was an extraordinary insight, arguably the most important theoretical prediction in the history of cosmology. Friedman had predicted the expansion of the universe 7 years before Hubble observed it. Einstein's reaction was dismissive. Upon reading Friedman's paper, he sent a brief note to the journal stating that Friedman's results appeared suspicious and that the solutions did not actually satisfy the field equations. In other words, Einstein believed Friedman had made a mathematical error. He had not. Friedman wrote to Einstein, carefully walking through his calculations and demonstrating that there was no error. Einstein eventually conceded, publishing a retraction of his criticism in the same journal. He acknowledged that Friedman's solutions were mathematically correct, but he still did not believe they described the real universe. He viewed them as mathematical curiosities, interesting but physically irrelevant. Friedman expanded on his work in a second paper in 1924, exploring the case of a universe with negative spatial curvature. He also published a popular book in 1923, World as Space and Time, in which he reflected philosophically on the meaning of his cosmological models. He wrote that the question of the universe's true nature would be decided by reliable data, a remarkably prescient statement. Tragically, Friedman did not live to see his prediction confirmed. In July of 1925, at the age of 37, he participated in a record-setting balloon flight, reaching an altitude of 7,400 meters. A few weeks later, he fell ill. He died on September 16, 1925, most likely of typhoid fever, though some sources suggest pneumonia. He was just 37 years old. Friedman's work was largely forgotten for years. It was published in a specialized journal in German by a relatively unknown Russian mathematician at a time when most physicists were focused on other problems. But his equations, the Friedman equations, would eventually become the foundation of modern cosmological theory. Every model of the expanding universe used by physicists today is built on the mathematical framework that Friedman laid down in 1922. History has not always given Friedman his due. The story of the expanding universe is often told as if it began with Edwin Hubble's observations in 1929. But the theoretical prediction came first, from a man who flew airplanes in wartime, tracked weather patterns in peacetime, and in between, found time to solve the deepest puzzle in the physics of the cosmos. And then there was Georges Lemaître. If Friedman provided the mathematical scaffolding for the expanding universe, it was Lemaître who gave it a physical interpretation, a narrative, a beginning. He was, in many ways, the most remarkable figure in this entire story. a Catholic priest, a combat veteran, a mathematical physicist of the first rank, and the person who, more than any other single individual, deserves the title of Father of the Big Bang. Georges Henry Joseph Edouard Lemaître was born on July 17, 1894, in the industrial city of Charleroi, Belgium. He was the eldest of 4 children in a devout Catholic family. His father, Joseph, was a lawyer. His mother, Marguerite, was a homemaker. From an early age, Georges showed a keen interest in both science and religion, and he would spend his entire life insisting that these two passions were not in conflict. Lemaître entered the Catholic University of Louvain in 1911 to study civil engineering. His studies were interrupted by the outbreak of the First World War, during which he served as an artillery officer in the Belgian army. He witnessed the horrors of modern warfare at close range, including, according to some accounts, the first poison gas attack in military history. The experience left a deep mark on him, though he spoke of it rarely. After the war, Lemaître changed course. He abandoned engineering and enrolled in the seminary, studying theology alongside theoretical physics. He was ordained as a Catholic priest in 1923. The same year, he received a scholarship to study at the University of Cambridge under the eminent astronomer Arthur Eddington. Eddington was one of the most respected scientists in the world. He had led the 1919 solar eclipse expedition that confirmed Einstein's prediction that light bends in the presence of a gravitational field, a result that made Einstein an international celebrity. He was also one of the foremost authorities on general relativity, and he was recognized in Lemaître as a student of exceptional brilliance. Years later, Eddington would describe Lemaître as a very brilliant student, wonderfully quick and clear-sighted, and of great mathematical ability. After a year at Cambridge, Lemaître crossed the Atlantic to study at the Massachusetts Institute of Technology, where he earned his doctorate in physics in 1927. During his time in the United States, he visited most of the major astronomical observatories, including Mount Wilson. He studied the latest observational data on galaxy distances and redshifts, familiarizing himself with the work of Hubble, Humason, and Slipher, and he began to see something that nobody else had quite put together. In 1927, Lemaître published a paper in the Annales de la Société Scientifique de Bruxelles, a relatively obscure Belgian academic journal. Written in French, the paper was titled A Homogeneous Universe of Constant Mass, and Increasing Radius Accounting for the Radial Velocity of Extragalactic Nebulae. In it, Lemaître independently derived the same expanding universe solutions that Friedmann had found 5 years earlier. But Lemaître went further than Friedmann. He explicitly connected the theoretical prediction to the observational evidence. Using Hubble's published galaxy distances and Slipher's redshift measurements, Lemaître showed that the data were consistent with a universe that was expanding at a rate proportional to the distance between galaxies. He even calculated a numerical value for the proportionality constant, the quantity we now call the Hubble constant, though Lemaître calculated it first. His estimate was not very different from the value Hubble would publish 2 years later. In other words, Lemaître had discovered the expansion of the universe before Hubble. He had derived the velocity-distance relationship that would become known as Hubble's law, and he had done so by combining theoretical physics with observational data in a way that was ahead of its time. But almost nobody noticed. The paper was published in French, in a journal that few international astronomers read. Lemaître sent a copy to Eddington, his former teacher, but Eddington apparently set it aside and forgot about it. When Hubble published his own paper 2 years later, in English, in a widely read American journal, it was Hubble who received the credit for the discovery. The question of priority in the discovery of the expanding universe is a sensitive one, and it has been debated by historians of science for decades. In 2018, the International Astronomical Union officially recommended that what had long been called Hubble's Law be renamed the Hubble-Lemaître Law in recognition of Lemaître's earlier contribution. The gesture was welcome, if long overdue. Lemaître himself never sought credit or complained about being overlooked. When his 1927 paper was translated into English and published in the monthly notices of the Royal Astronomical Society in 1931, the passages containing his derivation of the expansion rate were curiously omitted. For years, many suspected that the omission was the work of an editor seeking to protect Hubble's priority. But a 2011 investigation by the astronomer Mario Livio, who examined the original documents, concluded that it was Lemaître himself who had removed the relevant passage, apparently feeling that the data had been superseded by Hubble's more recent and more precise measurements. This was characteristic of the man. Lemaître was not interested in fame or priority. He was interested in understanding the universe, and his mind was already racing ahead to a question even more profound than the expansion itself. If the universe is expanding now, and if we run the clock backward, then at some point in the distant past, the universe must have been much smaller, much denser, and much hotter, taken to its logical extreme. This backward extrapolation leads to a moment when all the matter and energy in the universe was compressed into an incredibly tiny, incredibly dense state. In March of 1931, Lemaître published a brief report in the prestigious British journal Nature, in which he proposed exactly this idea. He suggested that the universe had begun in the decay of a single primordial superatom, or primeval atom, that contained all the mass and energy of the cosmos. The disintegration of this primeval atom, he argued, had given rise to space, time, matter, and the expansion that we observe today. It was the first scientific formulation of what we now call the Big Bang theory. The term Big Bang itself would not be coined until nearly 2 decades later, when the British astronomer Fred Hoyle used it dismissively during a 1949 BBC radio broadcast. Hoyle was a proponent of the rival steady-state theory, which held that the universe has no beginning and no end, and that new matter is continuously created to maintain a constant average density as the universe expands. Hoyle intended Big Bang as an insult. The name stuck anyway. Lemaître's idea was met with mixed reactions. Eddington, his former teacher, found it profoundly uncomfortable. He wrote that the notion of a cosmic beginning was philosophically repugnant, and that he hoped no such theory would prove correct. Einstein was more open-minded. In 1933, after Lemaître presented his theory at a seminar at the California Institute of Technology, Einstein reportedly stood up, applauded, and declared it the most beautiful and satisfactory explanation of creation to which I have ever listened. Though some historians have questioned whether Einstein was referring to the entire primeval atom hypothesis or only to a specific technical point about cosmic rays. Some scientists were suspicious that Lemaître's religious convictions had led him to formulate a theory that conveniently aligned with the biblical narrative of creation. Lemaître himself firmly rejected any such connection. He insisted that his faith and his science were entirely separate domains, and that the primeval atom hypothesis was a scientific theory based on physical evidence, not a theological argument. He once told a reporter, "As far as I can see, such a theory remains entirely outside any metaphysical or religious question." And in a remarkable act of intellectual courage, he even intervened when Pope Pius XII, in a 1951 address, attempted to claim the Big Bang Theory as scientific support for the Christian doctrine of creation. Lemaître quietly persuaded the Vatican to refrain from making such statements in the future. Lemaître spent the rest of his career at the Catholic University of Leuven, where he continued to refine his cosmological models and pioneered early work on electronic computation in astrophysics. He remained an active scientist and a devout priest until the end of his life. In December of 1964, at the age of 70, he suffered a heart attack and retired from his professorship. Shortly before his death, Lemaître received news that would have gratified him enormously. Two radio astronomers in New Jersey, working with a large horn-shaped antenna, had accidentally detected a faint, uniform hiss of microwave radiation coming from every direction in the sky. It was the echo of the Big Bang, the cooled remnant of the primordial fireball that had given birth to the universe. The primeval atom hypothesis, the theory that Lemaître had championed for more than 3 decades, had been confirmed. Georges Lemaître died on June 20th, 1966, in Leuven, Belgium. He was 71 years old. The detection of the cosmic microwave background radiation is one of the most serendipitous discoveries in the history of science. It happened more or less by accident at a telephone laboratory in New Jersey, and it almost did not happen at all. In the early 1960s, 2 young radio astronomers named Arno Penzias and Robert Wilson were working at the Bell Telephone Laboratories facility at Crawford Hill in Holmdel, New Jersey. They had been given access to a large, horn-shaped antenna that had originally been built to detect radio signals bounced off the Echo balloon satellites. The satellite system had been superseded by more advanced technology, leaving the antenna available for astronomical research. Penzias and Wilson planned to use it to study radio emissions from the Milky Way galaxy. To make the extremely sensitive measurements they needed, they first had to eliminate every possible source of interference. They accounted for the effects of radar and radio broadcasting. They cooled the receiver with liquid helium to suppress the thermal noise generated by the electronics. They painstakingly calibrated every component of the system, and yet, no matter what they did, they could not get rid of a persistent, low-level hiss. It came from every direction in the sky. It was the same intensity day and night, summer and winter, regardless of where the antenna was pointed. It corresponded to a temperature of roughly 3.5 degrees above absolute zero, a uniform microwave glow permeating the entire cosmos. Penzias and Wilson were mystified. They checked everything they could think of. They suspected the signal might be caused by the droppings of pigeons that had nested inside the horn of the antenna. They trapped the pigeons, removed them, and spent hours scrubbing the antenna clean of what Penzias later delicately described as a white dielectric material. The hiss remained. For months, the two astronomers were stuck. They could not identify the source of the signal, and they could not make it go away. Then, through a mutual acquaintance, Penzias learned that a group of theoretical physicists at Princeton University, just 60 kilometers down the road, were actually looking for exactly this kind of signal. Robert Dicke, a physicist at Princeton, along with his colleagues Jim Peebles, David Wilkinson, and Peter Roll, had been developing a theory that predicted the existence of a faint microwave glow left over from the very early universe. If the cosmos had indeed begun in a hot, dense state, as Lemaître and others had proposed, then the intense radiation from that early epoch should still be detectable today. Cooled by billions of years of cosmic expansion to just a few degrees above absolute zero, the Princeton group was in the process of building their own instrument to search for this radiation when they learned of Penzias and Wilson's mysterious signal. Dicke visited Bell Labs, examined the antenna, and listened to the hiss. He immediately recognized what it was. Returning to Princeton, he reportedly told his colleagues, with a mixture of admiration and resignation, "Boys, we've been scooped." The two groups published their results simultaneously in the Astrophysical Journal in 1965. Penzias and Wilson's paper, titled "A Measurement of Excess Antenna Temperature at 4,080 megacycles per second," simply reported the observation of the mysterious signal without offering a theoretical interpretation. Dicke and his colleagues published a companion paper explaining the cosmological significance of the detection. Taken together, the two papers provided the strongest evidence yet that the universe had begun in a hot, dense state and had been expanding and cooling ever since. The detection of the cosmic microwave background was the death knell for the steady-state theory. Fred Hoyle and his allies had argued for nearly 2 decades that the universe has no beginning and no end. In the steady-state model, the universe has always been expanding and will always continue to expand. But new matter is continuously and spontaneously created to fill in the gaps left by the receding galaxies, maintaining a constant average density throughout eternity. The idea had a certain philosophical elegance, and it had attracted a dedicated following among physicists who found the notion of a cosmic beginning distasteful. Hoyle, in particular, was a vocal and combative advocate, and his rivalry with the supporters of the Big Bang was one of the great scientific feuds of the mid-20th century. But the cosmic microwave background destroyed the steady-state model at a stroke. If the universe has always existed in more or less its present form, there is no reason for a uniform bath of microwave radiation to pervade all of space. The radiation makes sense only if the universe was once far hotter and denser than it is today. A prediction that follows naturally from the Big Bang theory, but has no place in the steady-state picture. The microwave background is, in effect, a photograph of the infant universe, taken roughly 380,000 years after the Big Bang. Before that moment, the cosmos was so hot that atoms could not form. Protons and electrons careened about in a blinding fog of superheated plasma, and photons could not travel more than a short distance before being scattered by the charged particles. But as the universe expanded and cooled, the temperature eventually dropped below roughly 3,000 degrees, cool enough for protons and electrons to combine into neutral hydrogen atoms for the first time. This process, known as recombination, suddenly freed the photons from their imprisonment. Light streamed outward in every direction, and it has been traveling through the expanding cosmos ever since, cooling all the while. By the time it reaches us today, 14 billion years later, those once blazing photons have been stretched by the expansion of space from visible light to microwave radiation, and their temperature has dropped from thousands of degrees to a mere 2.725 degrees above absolute zero. That is what Penzias and Wilson detected. They were listening to the oldest light in the universe, the cooled afterglow of the moment when the cosmos first became transparent. It is all around us, right now, in every direction. If your eyes could see in the microwave part of the spectrum, the entire sky would glow with this faint, uniform light. It fills every cubic centimeter of space, and it contains more photons than all the stars in all the galaxies combined. It is the most abundant radiation in the universe, and its existence is one of the most powerful pieces of evidence we have for the Big Bang. Penzias and Wilson were awarded the Nobel Prize in Physics in 1978 for their discovery. Dick, to the lasting frustration of many physicists, was not included in the prize. In the decades that followed, space-based missions, including NASA's Cosmic Background Explorer, launched in 1989, and the Wilkinson Microwave Anisotropy Probe, launched in 2001, would map the cosmic microwave background in exquisite detail, revealing tiny temperature fluctuations that served as the seeds of all the galaxies, stars, and planets in the observable universe. The microwave background also provided a powerful independent confirmation of the Hubble-Lemaître law. By measuring the properties of the background radiation, cosmologists could calculate the rate of expansion of the early universe and compare it to the rate measured by observing distant galaxies today. These comparisons gave broadly consistent results, but they also revealed a nagging discrepancy that would grow more troubling with each passing decade. A discrepancy we will come to shortly. But even as the cosmic microwave background cemented the Big Bang as the standard model of cosmology, it also raised deeply troubling questions that the original theory could not answer. The first was known as the horizon problem. When you look at the cosmic microwave background, it is astonishingly uniform. The temperature of the radiation is the same in every direction to a precision of roughly 1 part in 100,000. That uniformity might seem natural, even expected, but it is actually profoundly mysterious. Think of it this way. For two regions of space to reach the same temperature, they need to have been in contact at some point in the past. They need to have exchanged energy, just as a hot cup of coffee and the cool air around it gradually reach equilibrium. But when the cosmic microwave background was released, roughly 380,000 years after the Big Bang, the observable universe was already 90 million light-years across. Regions on opposite sides of the sky were so far apart that light, even traveling at its maximum speed since the very beginning, could not possibly have traveled from one to the other. They had never been in contact. They had no way of communicating. And yet their temperatures were identical. How was that possible? The second puzzle was the flatness problem. Measurements of the cosmic microwave background and other cosmological data consistently showed that the geometry of the universe is extraordinarily close to flat, not curved like the surface of a sphere, not warped like a saddle, but flat, like an infinite sheet of paper extending in every direction. In the framework of general relativity, the geometry of the universe is determined by its total energy density. If the density is above a certain critical value, the universe curves in on itself. If it is below that value, the universe curves the other way. Only if the density is exactly equal to the critical value is the universe flat, and the universe appears to be flat to a remarkable degree of precision. The trouble is that any slight deviation from perfect flatness in the early universe would have been amplified enormously over billions of years. For the universe to be as flat as we observe it today, its density at the moment of the Big Bang would have had to be fine-tuned to 1 part in 10 to the 60th power. That is an absurdly precise calibration, like balancing a pencil on its sharpest tip and having it remain standing for 14 billion years. These problems gnawed at physicists throughout the 1970s. The Big Bang theory worked beautifully in many respects, correctly predicting the existence of the cosmic microwave background, the abundances of light elements forged in the first minutes, and the observed expansion of the universe. But it offered no explanation for the uniformity of the background radiation, the flatness of space, or the absence of exotic particles called magnetic monopoles that certain theories of particle physics predicted should have been created in vast quantities in the early universe, but have never been observed. In 1979, a young physicist named Alan Guth was working at Cornell University, struggling to make a name for himself in the crowded field of particle physics. Guth had been born in New Brunswick, New Jersey, in 1947, and had grown up across the Raritan River in the small town of Highland Park. He had studied physics at the Massachusetts Institute of Technology, earning his bachelor's, master's, and doctoral degrees there, and then embarked on the long and uncertain trail of postdoctoral positions that defined the careers of so many young physicists of his generation. He had been at Princeton, then Columbia, then Cornell, then Stanford, always on temporary appointments, always searching for a permanent faculty position. It was a humbling existence for a brilliant mind, but Guth kept working, kept thinking, kept pushing at the boundaries of what was known. That autumn at Cornell, Guth was studying the magnetic monopole problem with a colleague named Henry Tye. Grand unified theories of particle physics predicted that the early universe should have produced enormous numbers of magnetic monopoles, particles carrying a single magnetic charge, yet none had ever been found. As Guth worked through the mathematics, he realized that if the very early universe had undergone a brief but extraordinarily rapid period of exponential expansion, it would have diluted any monopoles to the point of undetectability. They would still exist in principle, but they would be spread so thin across the inflated universe that you would never encounter one. And then the deeper implications hit him. On the evening of December 6th, 1979, Guth sat at his desk and worked through the calculations. If this exponential expansion had occurred, it would not only solve the monopole problem, it would also solve the horizon problem. Because the entire observable universe could have originated from a tiny region small enough for all its parts to have been in causal contact before inflation blew it up to cosmic scales, and it would solve the flatness problem, because inflation would stretch the geometry of space so dramatically that any initial curvature would be smoothed out. Just as the surface of a balloon appears flat when you inflate it to enormous size, Guth stayed up late that night, scribbling equations. When he was done, he drew a double box around the key conclusion in his notebook and wrote 2 words next to it: spectacular realization. He gave his first public seminar on the topic in January of 1980 at Stanford, where he had recently moved. In 1981, he published a landmark paper titled Inflationary Universe: A Possible Solution to the Horizon and Flatness Problems. The paper proposed that in the first unimaginably tiny fraction of a second after the Big Bang, somewhere around 10 to the negative 35th of a second, the universe underwent a phase of exponential expansion driven by the energy of a special quantum field. During this inflation, the universe expanded by a factor of at least 10 to the 26th power, and possibly much more in less than 10 to the negative 33rd of a second. It grew from something smaller than a proton to something larger than the entire observable universe today, in a time interval shorter than any human being could possibly comprehend. Guth's original model had some technical problems. The process by which inflation ended, what physicists call graceful exit, did not work properly in his initial formulation. But within a year or two, the Russian physicist Andrei Lind, working at the Lebedev Physical Institute in Moscow, and independently the American physicists Andreas Albrecht and Paul Steinhardt, developed refined versions of inflation that resolved these issues. Lind, in particular, proposed a variant called chaotic inflation that proved especially robust and versatile. These 4 physicists, Guth, Lind, Albrecht, and Steinhardt, are widely regarded as the architects of the inflationary theory. Inflation also made a crucial prediction about the cosmic microwave background. If inflation was driven by quantum fluctuations in the inflation field, the energy density of the early universe would not have been perfectly uniform. Tiny quantum variations, amplified to cosmic scales by the exponential expansion, would have left their imprint on the microwave background as minute temperature fluctuations. These fluctuations would serve as the seeds from which all the structure in the universe, every galaxy, every cluster, every vast cosmic filament, would eventually grow under the pull of gravity. When NASA's Cosmic Background Explorer satellite mapped the microwave background in 1992, it found exactly these fluctuations, variations of roughly 1 part in 100,000, distributed across the sky in patterns that matched the predictions of inflationary theory with remarkable precision. George Smoot, one of the leaders of the COBE team, famously described the result as looking at the face of God. The discovery earned Smoot and his colleague John Mather the Nobel Prize in Physics in 2006, and it transformed cosmic inflation from an elegant speculation into one of the cornerstones of modern cosmology. Later missions refined the picture further. The Wilkinson Microwave Anisotropy Probe, launched in 2001 and named in honor of the Princeton physicist David Wilkinson, who had been part of Dick's original team, mapped the fluctuations in exquisite detail over 9 years of observations. And the European Space Agency's Planck satellite, launched in 2009, pushed the measurements to even greater precision. Each new dataset confirmed the basic predictions of inflation and the Big Bang, painting an increasingly detailed portrait of the universe in its infancy. Inflation is now considered the leading explanation for the initial conditions of the Big Bang, though it remains a theoretical framework rather than a proven fact. There are many different models of inflation, and the precise physics of the inflatoned field remains unknown. Some physicists, including Steinhardt, one of inflation's original architects, have become vocal critics, arguing that the theory is too flexible, too accommodating of almost any observational result to be considered truly scientific. Others point to the extraordinary agreement between inflationary predictions and observational data as powerful evidence in its favor. The debate continues, and it is one of the most active frontiers of modern cosmology. But what inflation gave us, above all, was a mechanism for the Big Bang itself. It was, as Guth liked to say, a theory of the bang in the Big Bang. It explained not just that the universe was expanding, but how the expansion got started in the first place, and why the cosmos we observe today has the particular properties that it does. For most of the 20th century, the central question in observational cosmology was straightforward. How fast is the universe expanding? And is that expansion speeding up or slowing down? The logic was simple. If the universe is filled with matter, and if that matter exerts gravitational attraction, then the expansion should be slowing down over time. Gravity should be pulling the galaxies back toward each other, decelerating the outward rush. The key question was whether there was enough matter in the universe to eventually stop the expansion altogether, causing the cosmos to collapse back on itself in a big crunch, or whether the expansion would merely slow down and continue forever, with galaxies gradually drifting apart into the cold, dark void. For decades, astronomers tried to answer this question by measuring the deceleration of the expansion. They searched for a way to compare the expansion rate of the universe in the distant past, as revealed by very distant, and therefore very old, galaxies with the expansion rate today. The tool they needed was a standard candle, an object whose true brightness was known and consistent, so that its apparent brightness could be used to determine its distance. In the 1990s, 2 independent teams of astronomers found their standard candle in a particular type of stellar explosion called a Type 1a supernova. These supernovae occur in binary star systems, where a white dwarf star accumulates matter from a companion star until it reaches a critical mass and detonates in a thermonuclear explosion of staggering power. Because the explosion is triggered by the same physical process each time, the resulting brightness is remarkably consistent from one Type one supernova to the next. By measuring the apparent brightness of distant type 1 supernovae, astronomers could determine how far away they were. And by measuring their redshifts, they could determine how fast they were receding. The two teams, the Supernova Cosmology Project, led by Saul Perlmutter at the Lawrence Berkeley National Laboratory, and the Heisey Supernova Search Team, led by Brian Schmidt and Adam Rees, expected to find that the expansion of the universe was decelerating. The gravitational pull of all the matter in the cosmos should be slowing things down. They expected the distant supernovae to appear slightly brighter, and therefore slightly closer, than they would if the expansion were proceeding at a constant rate. What they found was the opposite. In 1998, both teams independently announced results that sent shock waves through the physics community. The distant supernovae were dimmer than expected, not brighter. They were farther away than they should have been. And the only explanation that fit the data was that the expansion of the universe was not slowing down at all. It was speeding up. The universe was accelerating. This was one of the most unexpected discoveries in the history of science. Everything physicists knew about gravity suggested that the expansion should be decelerating. Matter attracts matter. Galaxies pull on galaxies. The cosmic expansion should be running down like a ball thrown upward, gradually losing momentum under the relentless pull of gravity. Instead, something was pushing the universe apart, overcoming gravity and driving the galaxies away from each other at an ever-increasing rate. Nobody knew what this something was. They still do not, in fact. But they gave it a name: dark energy. Dark energy is the dominant component of the universe. It makes up roughly 68% of the total energy content of the cosmos, dwarfing both ordinary matter, about 5%, and dark matter, about 27%. And yet, we know almost nothing about what it actually is. One leading hypothesis is that dark energy is the energy of empty space itself, a kind of vacuum energy that pervades every cubic centimeter of the cosmos and exerts a gentle but relentless outward pressure. This idea is strikingly reminiscent of Einstein's cosmological constant, the very term he introduced in 1917 to keep the universe static and later abandoned as his greatest blunder. If dark energy is indeed the cosmological constant, then Einstein's blunder may turn out to be one of his most profound insights, just applied to the wrong problem. He introduced the constant to prevent the universe from expanding. It turns out the constant exists, but instead of preventing expansion, it is accelerating it. Perlmutter, Schmidt, and Rees shared the Nobel Prize in Physics in 2011 for their discovery. But the mystery of dark energy remains one of the deepest unsolved problems in all of physics, and the complications do not end there. In recent years, a growing tension has emerged in the measurement of the Hubble constant, the very quantity that describes how fast the universe is expanding. When astronomers measure the Hubble constant using local methods, observing Cepheid variables, and type 1 supernovae in relatively nearby galaxies, they get a value of roughly 73 kilometers per second per megaparsec. But when they measure it using cosmological methods, analyzing the cosmic microwave background radiation from the very early universe and extrapolating forward using the standard model of cosmology, they get a lower value, roughly 67.4 kilometers per second per megaparsec. The discrepancy, known as the Hubble tension, is too large to be explained by measurement errors. Both methods have been refined to extraordinary precision, and the disagreement persists. Observations from the James Webb Space Telescope, which has verified and confirmed the Hubble Space Telescope's measurements of Cepheid variables in distant galaxies, have only deepened the mystery. Something is off. Either there is an unrecognized systematic error in one or both methods, or there is new physics at work. Something about the universe that our current theories do not account for. Perhaps dark energy is not constant, but changes over time. Perhaps there was an additional burst of energy in the early universe, an early dark energy that temporarily accelerated the expansion and then faded away. Perhaps the universe is stranger than we have yet imagined. The Hubble tension is, in a sense, the latest chapter in the same story that began with Henrietta Leavitt and Vesto Slipher, and Edwin Hubble and Georges Lemaître. It is a reminder that the universe is under no obligation to conform to our expectations. Every time we think we have understood the cosmos, it reveals another layer of mystery, another depth that we had not anticipated. And so we arrive at the present day, more than a century after the first tentative measurements of galactic redshifts, and the picture of the universe that has emerged is both awe-inspiring and humbling. We live in a cosmos that is 13.8 billion years old, born in a cataclysmic event that brought space, time, matter, and energy into existence from a state of almost inconceivable density and temperature. In the first fractions of a second after that initial moment, the universe underwent a period of explosive expansion called cosmic inflation, during which it grew by a factor of at least 10 to the 26th power in less than a trillionth of a trillionth of a trillionth of a second. As it expanded, it cooled. Particles formed. Atoms formed. Light broke free. And that primordial light is still streaming through the cosmos today, cooled by billions of years of expansion to a temperature of just 2.725 degrees above absolute zero. The cosmic microwave background that Penzias and Wilson stumbled upon in their horn antenna. Over the following hundreds of millions of years, gravity pulled matter together into the first stars and galaxies. Those galaxies clustered into groups and clusters and superclusters, strung together in vast filaments and sheets separated by enormous voids, forming a structure that astronomers call the cosmic web. And all of it, every galaxy, every cluster, every filament and void, is embedded in a fabric of space that is stretching, inflating, expanding at every point. The observable universe, the portion of the cosmos from which light has had time to reach us since the Big Bang, is roughly 93 billion light-years in diameter. It contains an estimated 2 trillion galaxies, each containing hundreds of billions of stars. And all of those galaxies, with a few nearby exceptions bound together by gravity, are moving away from each other, carried apart by the relentless expansion of space. And now we know that the expansion is accelerating. Driven by dark energy, a force we cannot see, cannot touch, and cannot yet explain, the universe is not merely growing. It is growing faster and faster with each passing moment. The implications are staggering. If the acceleration continues, and if dark energy remains constant, then in the very distant future, the observable universe will contain fewer and fewer galaxies. The light from distant galaxies will be redshifted beyond detection. The cosmic microwave background will cool to temperatures indistinguishable from absolute zero. One by one, the stars will burn out. The galaxies will fade, and eventually, the universe will become a cold, dark, empty void, expanding forever into an infinite nothing. Physicists call this the heat death of the universe, and it is a profoundly lonely vision, but the journey there would be long and strange. In roughly 2 trillion years, the expansion of the universe will have carried all galaxies beyond the local group. The small gravitational neighborhood that includes the Milky Way, Andromeda, and a few dozen smaller companions. Beyond the cosmic horizon, their light will be stretched to infinite wavelength, redshifted into oblivion, and they will simply vanish from view. By then, the Milky Way and Andromeda will have long since merged into a single enormous elliptical galaxy that astronomers have already named Milkdromda. That merged galaxy will drift in an emptying void, surrounded by darkness, with no evidence remaining of the billions of other galaxies that once populated the observable universe. The cosmic web, that magnificent scaffolding of filaments and clusters that stretches across hundreds of millions of light years, will dissolve into nothingness as its constituent galaxies sail past the horizon one by one. Any civilization born in that distant epoch would look out at the sky and see only their own stars. They would have no way of discovering that the universe is expanding, because there would be nothing left to see expanding away from them. The very evidence that allowed Slipher and Hubble and Lemaître to deduce the expansion would have been erased by the expansion itself. And then, the slow decline of the stars would begin. In roughly 100 trillion years, the last stars will exhaust their nuclear fuel and flicker out. The universe will be populated only by the cold remnants of stellar corpses, white dwarfs cooling toward absolute zero, neutron stars slowly spinning down, black holes evaporating over inconceivable timescales through a process Stephen Hawking described in 1974. Even the protons that make up ordinary matter may eventually decay. If certain theories of particle physics are correct, leaving the universe as nothing but a thin bath of photons, neutrinos, and electrons, all drifting farther and farther apart as space continues its relentless expansion. It is a future of ultimate isolation, where even the light of the most distant stars can no longer bridge the growing emptiness between them. In such a universe, an astronomer born 100 trillion years from now, if such a being could exist, would look up at the night sky and see nothing. No galaxies, no distant pinpoints of light, only darkness. They would have no way of knowing that the universe had ever been anything other than dark and empty. They would have no evidence that the cosmos had once been ablaze with the light of trillions of galaxies, that the night sky had once sparkled with the reflected glory of 100 billion stars in a single galaxy alone. The very evidence of the expanding universe, the redshifted light of distant galaxies, the cosmic microwave background, the abundance of light elements forged in the first minutes, would have faded beyond all possibility of detection. The cosmic microwave background itself, that ancient whisper that Penzias and Wilson heard in their horn antenna, would have been stretched by the expansion to wavelengths longer than the observable universe itself, utterly undetectable by any conceivable instrument. The primordial helium and deuterium would still exist in the burned-out stellar remnants, but without galaxies to observe and compare, without a cosmic background to calibrate against, there would be no way to infer that those elements had been forged in a hot, dense beginning. The great discoveries of Slipher and Hubble and Lemaître and Penzias and Wilson, the painstaking accumulation of evidence that revealed the expanding universe, would have been, in principle, impossible to replicate. The universe, in its final state, would have hidden its own history. In a sense, we are living in the golden age of cosmology. The universe is still young enough, still bright enough, still filled with enough observable evidence for us to piece together its history, from the first fractions of a second to the present day. That window will not last forever. And so there is something urgent, even poignant, about the work of the astronomers and physicists who have spent the last century deciphering the story of the expanding cosmos. They are reading a message that the universe will eventually erase. But that future is unimaginably far away. Trillions upon trillions of years, at the very least. And between now and then, there is time. Time for stars to be born and die, and be born again from the ashes of their predecessors. Time for planets to coalesce from swirling disks of gas and dust. Time for life to arise and wonder, and ask the kinds of questions that have driven this entire story from the very beginning. Time for us to look up at the night sky and marvel at the fact that we exist at all. In a universe that is not standing still, in a cosmos that is not eternal and unchanging, but dynamic, evolving, restless, alive with possibility. 100 years ago, we did not know any of this. We thought the Milky Way was the whole universe. We thought the cosmos was static. We thought space was just an empty stage on which the drama of physics played out. The stars seemed fixed and eternal, and the great philosophical questions about the origin and fate of the universe seemed beyond the reach of science. And then, piece by piece, person by person, discovery by discovery, the picture changed. A woman in a basement at Harvard, bent over photographic plates while her hearing slowly faded, noticed that brighter stars pulse more slowly. She never knew the full significance of what she had found, and she died before the world recognized her contribution. But her work gave us the ability to measure cosmic distances for the first time. A quiet farmer's son in the dry desert air of Arizona, working with a temperamental spectrograph on a 24-inch refractor, measured the light from distant nebulae and saw that it was red. He was cautious and private and never sought the spotlight. But his meticulous observations provided the first direct evidence that the cosmos was in motion. A brilliant Russian mathematician who had flown bombing missions in the First World War and survived the chaos of revolution, sat down with Einstein's equations and showed that the universe must be expanding. He died of illness at 37, and his prediction was forgotten for years. But his equations became the foundation of everything that followed. A Belgian priest with a gentle demeanor and a first-rate mind read those same equations and reached the same conclusion, independently and with even greater clarity. He presented his results to Einstein himself, who dismissed them. But he persisted, and eventually the world caught up. a young astronomer on a mountaintop in California, a man who had studied law at Oxford and boxed in his youth, pointed the largest telescope in the world at a fuzzy patch of light in the constellation Andromeda and found another galaxy. Then he measured the distances and velocities of dozens more, and the pattern was unmistakable. The universe was expanding, and two radio engineers in New Jersey, trying to calibrate a horn antenna for satellite communication, heard a persistent hiss that they could not eliminate no matter what they tried. They even chased the pigeons from the antenna and cleaned up their droppings. The hiss remained. It turned out to be the echo of the Big Bang itself, the oldest light in the universe, cooled by 14 billion years of expansion to a whisper, just barely above the silence of absolute zero. Each of these discoveries built on the ones that came before. Each required a different kind of courage, the courage to challenge the prevailing wisdom, the courage to trust the mathematics, the courage to publish results that seemed absurd, the courage to spend years doing painstaking, tedious work in the hope that it might matter. The story of the expanding universe is the story of human curiosity pushed to its absolute limit. It is the story of men and women who refused to accept the universe as it appeared and insisted on knowing the universe as it actually is. It is a story that is not yet finished. The Hubble tension is real. Dark energy is unexplained. The ultimate fate of the cosmos is uncertain. Cosmic inflation remains a theory without a confirmed mechanism, and somewhere, right now, someone is pointing a telescope at the sky and measuring something that does not quite fit, some small discrepancy that might, if pursued with sufficient care and courage, reveal the next great truth about the nature of reality. We live in an expanding universe. We have lived in one since the moment it was born, and the human mind, against all odds, has expanded with it, reaching outward from a small blue planet orbiting an ordinary star on the outskirts of an ordinary galaxy, to comprehend the shape and history and fate of the cosmos itself. That is no small thing. In fact, in all the 14 billion years since the universe began, it may be the most remarkable thing that has ever happened. A cosmos that began in silence and fire somehow gave rise to minds that could reconstruct the story of that fire, measure its fading glow, and wonder what comes next. You have been watching the entire history of the universe. If you enjoyed this journey through the cosmos, do not forget to like and subscribe and leave us a comment to tell us what you think. Thanks for watching, and we will see you next time.